Hello everyone. Today we're going to talk about plastic ethanol stills. There seems to be a shortage of information on YouTube about plastic stills, so this is our open source contribution. First, of course, we got to cover the legal disclaimer. In the USA, brewing beer and wine for personal consumption is generally legal, but not everywhere. I think in Florida, for example, anything over 1 gallon is a problem. In the USA, it is illegal to possess a still of any kind whose intended purpose is the distillation of spirits, alcoholic beverages, in other words. Still equipment for fuel alcohol is legal if the proper permits are obtained and safety standards followed. Always comply with local government regulations for legality and safety. If any questions, consult a lawyer or regulator. So, what is the motivation for using a plastic still? I mean, why not just use steel, stainless steel, or copper? Well, let's look at some of the economic factors of fuel ethanol versus moonshine, spirits, drinking alcohol, alcoholic beverages. For one factor, the price or value of the product, the alcohol that's produced. Spirits, the value is very high. Let's say $10 a liter or even more for high quality spirits. For fuel ethanol, the value is very low. Maybe 50 cents a liter at current oil prices. The quantity needed, we could understand that fuel ethanol, we need a lot more than drinking ethanol per day. As an estimation, I used 1 liter per day for spirits, but we would need, let's say, 20 liters per day for fuel ethanol. So we need a lot more. What's the proof that's needed? For spirits, we need 80 proof. That's about the proof of vodka, a little higher for gin. That's enough for drinking. Anything higher than that becomes a poison. For fuel ethanol, we need 180 proof, 190 proof. If we expect to mix it with gasoline, we need 200 proof, or 195, or even higher. So the proof is very much higher for fuel ethanol than spirits. So all of this translates into the number of plates we need in our still. For spirits, at 80 proof, we can generally get away with 4 plates. But for fuel ethanol, we need at least 8 plates. And if you want to try to do a continuous still for higher production and more efficiency with a fractionation and a stripping section, you need maybe 16, 18, maybe 20 plates if you want to really hit it hard and have continuous good product. So the economics of spirits looks okay. The value is high, the net needed quantity is low, the proof is low, and we can get away with smaller equipment. It looks fine. But frankly, the economics for fuel ethanol, low value product, we need a lot of it. It has to be very high proof. We need large equipment. The economics are, frankly, ridiculous. You just cannot justify spending, big money, $50,000 on a big still for fuel ethanol, while you could do it for spirits. You just can't for fuel ethanol. So let's look at some common plastics. PVC is very common. The problem with PVC, it has a very low melting point. It gets very soft at only maybe 60 degrees. CPVC is much better. We have acrylic, ABS, polyethylene, polypropylene, and polypropylene copolymer, which is PPR. Some of these are suitable for stills. CPVC would be okay. Polyethylene is probably okay. Polypropylene and PPR seem to be okay. And PPR, which is polypropylene copolymer, has the highest chemical resistance and also the highest melting point. What is PPR? PPR is short for polypropylene random copolymer. It's formed by extrusion, and small parts can be injection molded. It's a thermoplastic, meaning when you make it hot, it melts. When you make it cold, it solidifies, and that cycle is repeated as often as necessary. PPR process uses a gas polymerization process to make about 5% polyethylene in the molecular chain of PP, random polymer. That's why they call it random copolymer. This new plastic has properties better than either PP or PE. PPR has good impact resistance and good long-term creep properties. PPR is non-flammable, its surface is non-wettable, it has a very low surface tension, it repels water, and it's also not gluable. You cannot use glue, you have to use plastic welding techniques to bond it. So let's look at some of the chemical compatibility issues. We agree, ethanol distillation represents a very harsh environment to most plastics. We have hot ethanol, we have hot methanol, acetic acid. If your fermentation wasn't going properly, we have a little bit of acetone. These are in very low quantity, but they are there. PPR has very good chemical resistivity for these chemicals. Ethyl alcohol at 96% concentration, it gets an A all across the board up to 80 degrees C, which is the boiling point of ethanol, a little bit higher than that. Methyl alcohol gets an A. This dash means they just don't have data. It doesn't mean it failed. It means there's just no data on that. Acetic acid gets an A. Acetone gets an A. At very high concentrations, 100%, 10%, and 100%, we are nowhere near that concentration. So according to this data, PP and PPR should be fine. Let's look at the thermal characteristics. The welding temperature of PPR is 265 degrees C. That's quite hot. The melting point is greater than 160 degrees C. The Vicat softening temperature, which is controlled by this specification, which you can look it up, is 130 degrees C. What they do is they take a very small probe with a cross-sectional area of about 1 square millimeter, and they put a load on it of about 1 kilogram, and they press it into a flat piece of this material, PPR material, and then they heat the whole thing up slowly at a certain ramp in temperature, and when that probe penetrates to 1 millimeter, that's what they say is the Vicat softening temperature, when the probe penetrates 1 millimeter into the base material. Hospitals generally agree that PP is autoclavable up to 121 degrees C. Hospitals use a lot of PP, polypropylene utensils, and every kind of instrument is all PP, and they autoclave them at 121 degrees C with no ill effects. And PPR has very low heat conductivity. Heat conductivity is not good for us in the fractionation column because it's just inefficient, and it also it requires us to use a taller column. Copper has very high heat conductivity. The units are watts per meter degree Kelvin. Copper has 400, has a reading of 400 in those units. Stainless steel is much lower, maybe 25 times lower, at only 16 watts per meter degree Kelvin. And PPR is much lower than that at 0.24 watts per meter degree Kelvin. We did a thermal analysis of the wall temperature. Now, if a piece of plastic is inside an environment that is at a certain temperature, let's say, for example, the autoclave, the temperature of the PP will quickly equalize to the surrounding temperature. But in our case, we have a wall of PP material. On one side of the wall, in an extreme case, or the worst case analysis, we have boiling water on one side, and we have air on the other side. So I hired a guy on Fiverr to do a thermal analysis to tell me the temperature across the wall. And I made it a worst case scenario. We have boiling water, which in fact we won't, right? Because we'll only have it, at the most it will be maybe 95 degrees C at the bottom of the column, and maybe 85 degrees C at the top of the column or so. And the outside air was 30 degrees C and gently rising due to convection. The D is the thickness of the tank. And the report is on the website, but the calculations showed that the outside wall temperature would only be about 60 degrees or a little bit less than that. And the temperature gradient is linear. So that means that most of the wall will be way below any kind of softening temperature. And based on this data, again, we believe the column will not get soft, it won't bend, it will be self-supporting. Here's the long-term reliability chart from the manufacturer of PPR pipes. Our usage will be around 95 degrees C, but you see they even include 110. But okay, let's look at the 95 degrees C curve. And this is the time to failure. 1 year is here, 5 years, 10 years, 50 years is here. The way you use this chart is you look up your system pressure, You go across till you hit your operating temperature, and then you see the lifetime. Now, the problem with this graph is it only goes down to 0.5 megapascals, and that works out to be about 2,000 inches of water, which is a very high pressure. It's about 5 atmospheres. Our still will be operating at a very, very low pressure compared to this. The top of the still is essentially open to the atmosphere, so the pressure is essentially zero. And as we come down the column, each plate will be at a slightly higher pressure, but it's only maybe an inch of water due to the bubble caps forcing the air to go below the water level about an inch. So that will create some back pressure, but it's very, very low. The column maybe has a total of 20 inches of water back pressure. And don't forget, 1 atmosphere, 14.7 psi, is 33 feet of water. And again, we're talking about 20 inches of water pressure. So our system pressure is very, very low. It's way off the chart down at the bottom. So again, based on this, we're expecting our system will last the 50 years that the material is expected to last, 50 years. So some of the still requirements: safety. We've shown that there's no chemical concerns. We have good chemical compatibility, and it resists all the known chemicals in mash. There's no thermal concerns. We're not near the melting temperature or the softening temperature. We have low thermal conductivity for good efficiency. There's no contamination to the end product, no volatile compounds to leach out, similar to what could happen with PVC and plasticizers and so forth and so on. Low cost, much lower than stainless steel or copper. Easy fabrication, very easy, green check mark. Long life. Modular, we're going to make the system compatible with existing tri-clamp arrangements, and we're going to have a viewing window. So here's our concept. We are going to use the existing components that you might have. You might have a bubble plate or perforated plate and the seals. We are going to machine the surface of the plastic to mate with the existing components. We're going to have a viewing window. The thickness of the wall is thick enough we can just machine this flat, put a seal here, use a glass and a cover. The latches are simple latches. We don't want to use the tri-clamp latches. The tri-clamps are very nice, very, very nice, but they're made for systems at higher pressure, steam pressures, 5, 10 atmospheres. They're really overkill for what we need, and they're expensive. For the larger diameter tri-clamps, you might spend $25, $35, $40, $50. For a large system like we're talking about with 20 plates, 15 to 20 plates, you could spend $2,000 just on clamps. So we're going to use toggle clamps, much cheaper and certainly adequate for our needs. So the conclusion is PPR is a good choice for plastic stills. Later on, we'll probably investigate also CPVC due to its good availability. Everything we're going to do here is open source. All the drawings will be on the website. We have an open forum, free and open to all. We welcome discussions on plastic. You can visit our website, ppstills.com. The one thing to do right now is we're just getting started, so sign up for the mailing list, and we'll keep you updated on developments once in a while. We're going to offer 35% discount for distributors. And thank you for watching. Hope you enjoyed this content.